In cross moments, we will discuss the generating function for the random vector. Earlier we have discussed generating functions for the random variable, that is a probability generating function for a random variable, then moment generating function for the random variable, then we have discussed the characteristic function for the random variable. Now we are going to discuss these generating functions for the random vector. So that is the first definition. Let capital X be a random vector whose elements are x1, x2 and so on, xn, be a n dimensional random vector with joint probability mass function, that is a p of x1, x2, xn as a function of x1, x2, xn. Then one can define the probability generating function of a random vector is defined as, we use the notation G suffix x, here the x is a vector, whose elements are s1, s2, sn. We have defined earlier the probability generating function of a random variable. In that case we have G suffix x as a function of s. Now we have a random vector, therefore it is a function of n variables s1, s2, sn. That is same as summation of a joint probability mass function of x1, x2, xn as a function of x1, x2, xn multiplied by s1 power x1, s2 power x2 and so on, sn power xn. And here the summation is over all the xi's without restriction. So this is going to be a function of s1, s2, sn. This is called the probability generating function of a random vector, and this is for absolute of s1 is less than or equal to 1 and so on till absolute of sn is less than or equal to 1, provided the series, the right hand side series is convergent. So as long as within the interval of absolute of s1 is less than or equal to 1 and so on, absolute of sn is less than or equal to 1, the right hand side series converges, then that is going to be called as a probability generating function of a random vector. From the probability generating function of a random vector, one can get the probability generating function of any one random variable also. That is, suppose I want to find out the probability generating function of a random variable x1. That is same as by substituting the probability generating function of a random vector in s1, you keep it s1, whereas s2 onwards you substitute the value 1 till 1, you will get the probability generating function of a random variable x1. Similarly, you can get the probability generating function of other random variables. In this way you can get the probability generating function of a fewer random vector also by substituting all other variables as 1. The next result, suppose xi's are independent random vectors. Suppose the random variables are independent, then you can replace the joint probability density function by replace joint probability mass function by probability mass functions of xi's, since they are independent random variable. Therefore, this summation will simplified into the probability generating function of a random vector as a function of S1, S2 and so on. That is going to be product of probability generating function of each random variable from I is equal to 1 to n, because the joint probability mass function can be replaced by the product of probability mass functions of individual random variable. So, the right hand side g suffix xi, that is a probability generating function of the random variable xi. In this way, sometimes we may be interested to find out the probability generating function of sum of random variables as a function of S. That is same as, if you apply the same concept, that is same as since they are independent random variable, that is going to be the product of I is equal to 1 to n, the probability generating function of individual random variable with the variable S. When xi's are independent random variable, the first one is a probability generating function of a random vector. The second expression is probability generating function of sum of random variables, that is a one random variable with the variable S, that is same as the product of probability generating functions of individual random variable. We will go for the second definition, that is moment generating function of a random vector. Let x be a vector whose elements are x1, x2, xn, be a n dimensional random vector if there exist m which is greater than 0, such that the expectation of exponential of random vector x multiplied by t transpose, that is finite for all t where t is a vector whose elements are t1, t2 and so on, that is belonging to Rn, with the norm of t is defined as, it is a Euclidean norm, that is t1 square plus t2 square and so on plus tn square, and that quantity is going to be less than capital M. If this condition is satisfied, then one can define the joint moment generating function of a random vector with the notation m suffix x, x is a vector, small t, that is also vector, whose elements are t1, t2, t2, that is nothing but expectation of e power exponential of the vector x, vector t transpose, and this result is valid only for norm of t is less than capital M. So, this is going to be called as a joint moment generating function of a random vector. Here also we can go for, suppose these random variables are independent. Suppose these xi's are independent random variables, then it is going to be same as the moment generating function of a vector as a function of vector, that is going to be product of I is equal to 1 to n, the moment generating function of individual random variable with the variable ti. Ti is not a vector, ti is an element. When these random variables are mutually independent. Similarly, one can go for sum of random variables. Similarly, one can go for, suppose I want to find out the MGF of sum of random variables as a function of t. Here the t is a variable, not the vector, but I am making the assumption xi's are independent. Again, this is going to be, if you substitute in the definition and do the simplification, you will get a product of MGFs of individual random variables with the same variability. Suppose I will make a additional condition, suppose xi's are IID random variables, that means independent and identically distributed random variables. In that case, the moment generating function of sum of random variables for the identical distributed random variable, the MGFs are also going to be identical. Therefore, you find out the MGF of any one random variable as a function of t power n, because all the random variables are identical. Now, we will move to the third definition, that is the joint characteristic function of a random vector. Again, the same way, let x be a random vector whose elements are x1, x2, xn, be a n dimensional random vector with the t is a vector whose elements are t1, t2 and so on tn, that is belonging to Rn. You can define the joint characteristic function of a random vector capital X denoted by psi suffix x, x is a vector, as a function of t, t is also vector, that is same as expectation of exponential I times vector x, vector t transpose, where I is the square root of -1. Here you do not need any provided condition, similar to the characteristic function of a single dimension random variable. So this is a characteristic function of a, this is a joint characteristic function of a random vector. So whatever we discuss the results on independent IID random variables and so on, everything will be satisfied for here also. Therefore, no need to do the simple results what we have done it for the moment generating function, because it is just replacing t by I times t. Therefore, we leave it as it is with the definition. In the later, when we are solving the problems, we are going to use a joint probability generating function of a random vector. Similarly, we will be using a joint moment generating function of a random vector and also joint characteristic function of a random vector. Therefore, here I stop it with the definitions and the simple results.